Hi, welcome to my channel. In the previous video tutorial, we observed that the random forest model was overfitting. We also observed that the GEDI L4A dataset that contains the above ground biomass density ranged between 0.87 megagrams per hectare to about 228 megagrams per hectare, which is too high for the study area. In this video tutorial, we will minimize the overfitting by improving the quality and quantity of the training dataset. So let's get started. First, we must initialize and authenticate the Earth engine as we have done in the previous video. Then we are going to import the necessary Python libraries that we are going to use to process and analyze the datasets. Following that, we are going to import all the datasets that we are going to use. First, we are going to import the project boundary areas using the World Database on Protected Area database. And then following that, we are going to load the Sentinel-2 spectral reflectance data. Then we will derive the spectral indices as we have done in the previous video. Following that, we are going to load other datasets such as slope and elevation. Okay, I've also shown you how to do this in the previous video. Then we are going to merge all the predictor variables, that is the Sentinel-2 dataset, the spectral indices, elevation, and slope. We're also going to make sure that we clip this merge collection to our project boundary so that all the data sets have got the same dimension. Right, so now I'm going to focus my attention on improving the quality and quantity of the GEDI training dataset. Okay, so as we have noted previously, we have a very high variability of the GEDI L4A dataset. So how would we improve this dataset? As we have seen in the previous video, I've said that we are taking the GEDI L4A dataset between January and May, which is the peak of the biomass growth in the project study area. Right, so what do we want to do? First, we want to improve the quality of the GEDI dataset by using three functions that we are going to define. So the first function is the quality max function, which is responsible for just selecting the highest quality GEDI data. So here we are going to use the quality flag and then the degrade function to do that. Right, next we are going to use the error mask function, which is going to remove those GEDI measurements with a relative standard error above 50%. Okay, then finally we are also going to use the slope function, which is going to mask out those GEDI points that falls on slopes that are greater than 30%. Right, after that we also want to increase the number of points of the GEDI points in the project area. So here we are going to define scale. When we do our sampling, we are going to define scale at 10. In the previous video, we have defined scale at 30. So by improving the resolution at which we sample our data, we also increase our GEDI data points. And then finally, we also want to calculate the summary statistics so that we check the mean, median, standard deviation, the minimum and maximum. So after we run this code, we see that the mean above ground biomass density is 55 megagrams per hectare, while the median is 54. We have standard deviation at 24, and we have a change in the minimum above ground biomass density, which is now 6 megagrams per hectare from the previous of 0.87. So here we notice a change. However, the maximum above ground biomass density is still high at 228. And then we have significantly increased the number of the GEDI training points. So here we have about 33,408 for the whole study area. Right, following that, we just want to display the points on the map. Okay, then next we still need to continue the data cleaning. So before we do that, we want to perform an exploratory data analysis. This allows us to check the density and box plots so that we notice how our data is distributed. Right, so if we run this chunk of code, we see these graphs which shows the distribution of the above ground biomass values. As you can see, the histogram and density plot shows that the data is mostly distributed or concentrated between 0 and 100. So we have between 0 and mostly 0 and 100 megagrams per hectare. And also we notice that the box plot shows that there are many outliers above 100. So these are the values that are out of a range. So we need to take care of this. In addition, following the literature review, we can see that in most research in the study areas that have the similar vegetation conditions, they show that usually the mean above ground biomass density is around 56 megagrams per hectare, while the minimum ranges, while the above ground biomass values ranges between the minimum of say 11 megagrams per hectare to about 95 megagrams per hectare. Therefore, we need to filter these. We need to filter the GEDI points so that we have an appropriate range of values that we are going to use. So for the data cleaning, we are going to specify that we want the above ground biomass density to be between 6 megagrams per hectare to about 90 megagrams per hectare. Right, if we run this, we can also display the points that we have filtered. And next, we also want to check the density and the box plot so that we check how the data points are distributed. Right, as we can see here, we now have a major concentration of the values between 6 and 90 megagrams per hectare, and we have eliminated most of these outliers. Right, so following that, we are going to do the data splitting as we have done in the previous video. We are going to have 70% for training and 30% for testing. So here we have got about 21,579 GEDI sample data points for training, and then 9,206 GEDI data points for testing. Following that, we also conduct sensitivity analysis. Why do we need sensitivity analysis? We want to determine how the changes in the scale, by scale I mean here the spatial resolution, affect the random forest model outcome. So this is going to help us identify the most appropriate scale that balances the detail and then the generalization of the random forest model. Please take note that this procedure takes a bit of time depending on the size of your project area or study area. So here I've defined the range of scale to be between 10 and 200. I've just done this for the purpose of the demonstration. I've defined the scale ranges to be 10, 20, 30, 50, 100, and 200. You can change these numbers to suit your study area. And then here for the predictor variables is we have used in the previous video. We have the Sentinel-2 bends, the spectral indices, the elevation and slope. And our target variable here is above ground biomass density from the cleaned GEDI data points. And then we create a function that is going to analyze the scale, and we are also going to define the random forest model. Here I've just put the number of trees to be 50 so that we don't spend much time running the model. So if we run this code, we are going to get our model results. As we can see from the model results, the base scale here at which we get the lowest RMSE, and R squared is at 50. So at 50 we can get the best model. Right, following that we can plot sensitivity analysis graph. We can plot a sensitivity analysis graph so that we can visualize the results. So as you can see, the RMSE here starts very high and then drops at 50, and then we have increase as the resolution increases. And the same for the R squared. We have a very low R squared, and as we go to about 50 meters, we have the best R squared, and then the model decreases. So this just gives you an idea of what we can do when we want to check at which scale or resolution can we have our best model. Right. Finally, we can display the various maps or the above ground biomass maps that we have predicted, so that we can compare. Okay, so here we have the different maps at different spatial resolution. Okay, let's just check. Okay, so this is for the first resolution, then second, third, fourth, fifth, and then the final one, which is 200. So it can give us an idea of how the model performs at different spatial resolution. Right, so this is quite important to do a sensitivity analysis. Here I've just done the sensitivity analysis using the scale so that we understand how the model performs at different scales. Right. This concludes this part of this video tutorial where we wanted to improve the problem of overfitting and improving our model. Thank you very much for watching this video tutorial. If you like this video, please give it a thumbs up, and please subscribe so that you get an alert if I have more videos tutorial in the future. See you in the next video. Bye.